Hello, my name is Jiashang Liu, and I'm today's presenter. I'm from the Ohio State University. Today, I'm going to talk about our work, Fundamental Limits of Approximate Gradient Coding. So this is a joint work with my colleague, Snow Wang as the first author, and our advisor, Professor Nashroff. Let me start with some basic background. Most machine learning tasks aim to solve the following problems, which tries to find an optimal classifier W such that the objective function is minimized. So here we have a data set with n data points, x1, y1 to xn, yn. L is the task-specific loss function, and R is the regularization function. So typically, to solve this problem, we use the following gradient-based approach. In each iteration, we update the new value of the classifier vector W by using this equation. So HR is the proximal mapping, which depends on the regularization function. So notice that here, GI is the gradient evaluated at I data partitions, and we need to compute all the gradients among all the data points. In industrial applications, it contains a data set with like more than 1 billion data points. So to increase the learning speed, the data is usually partitioned and distributed into multiple workers. So we have, for example, we have this master-slaver structure, and in each iteration, the master node first broadcasts the new vector W to each worker. And each worker evaluate a partial gradient and send the results back to the master node. The master node then update the new vector W by taking the sum of the gradient, partial gradients and do the mapping. So finally, the algorithm iterate multiple times and terminate until the classifier W converges. Let's look at the data parallelism again and see the improvement from the distributed computing. So in the chaining of neural networks, we will bypass the chaining data into the neural network multiple times. So suppose that the time of passing the whole data set in the machine is t. Then after we split the data into a number of n partitions, ideally, the chaining time of each local machine is t over n, and the overall time is reduced by a factor of n. However, the gain from distributed chaining is far from ideal. So here is an experiment of the data parallelism in Google Cluster. So it plots the chaining time to achieve 16 accuracy versus the number of machines. We can see that even we distribute the data into more than 3,000 machines, it can only provide less than 5 times speed up. So you may ask why this phenomenon happens. So let's talk about the general coded distributed optimization framework. Each worker stores multiple data blocks, and during one iteration, each worker computes a linear combination of a partial gradients and send the results back to the master node. The master node decodes the sum of the gradient after collecting part of these results. So due to the network conditions, scheduling, strategy, and so on, some workers may not be able to compute the partial result and send the results back to the master node immediately. And these workers, which we call them strugglers, can have an extremely bad impact on the chaining speed. So here comes the problem. How can we design the data partitioned encoding scheme, meaning that how to assign different computation tasks to each worker in order to avoid the delay from the strugglers? So we introduce the following matrix notations of the gradient coding problem. So consider we have a distributed system with n workers, and among these n workers, s of them are strugglers, and we partition the data into n data partitions. A gradient coding scheme can be represented by an m times n coding matrix M, and each worker computes a linear combination of gradients. So for example, G tilde I is the linear combination, is the computation task for the worker I, and Mij is basically the coefficient of the original gradient Gj. So the goal is to recover the full gradient or the sum of the gradients from any m minus s workers. So here we can define the computation load as the number of non-zero elements in matrix M, which directly measures the number of partition gradient evaluation in each worker in this problem. So the key property of the problem is that we aim to recover the sum of the gradient instead of each partial gradient. So therefore, we need a different property of the coding matrix. Suppose that we receive the results from worker I1 to In minus s. We can represent the received result by the following metric notation. This is the receive coding matrix, and then we can see that the coding is based on solving the following equation. The intuition is that we are trying to find a linear combination of codic partial gradient that is equal to the sum of gradient. So to guarantee the decodability of any m minus s results, we need that the span of any m minus s by n submatrix contains all one vector. So based on this theoretical intuition, the initial work by Tadon shows that the minimum computation load of each worker is s plus 1 in order to resist any s strugglers. And they design a cyclic MDS code which can exactly match such load bound. However, as we discussed before, the computation load is linearly dependent on the number of strugglers. It will cause large computation and storage overhead when the number of strugglers is large. Therefore, they propose the idea of approximate gradient coding. Instead of exactly recovering the full gradient, we can recover the gradient with a bounded error. So this is motivated by the fact that the gradient descent is robust to noise. Based on this idea, existing works have constructed several schemes that can achieve a computation load of O log n and an error of n over n minus s log n, which is significantly lower than the cyclic MDS code. So therefore, the research community posed a new open problem, that is, what is the optimal trade-off between the computation load, recovery, error, and struggler tolerance in this approximate gradient coding problem. So to answer this question, let's first consider a simplified scenario. We consider the gradient coding scheme that can exactly recover the full gradient with high probability. So this can be regarded as a probabilistic realization of the worst case scenario. So formally, we showed assumed that suppose out of n workers, S equals delta n are strugglers, then the minimum computation load satisfies the following inequality. So it can observe that the lower bound is dependent on the struggler tolerance. For example, if S equals n to the power alpha, the lower bound is actually a constant 1 over 1 minus alpha. If S is proportionally to N and C is a constant, then the lower bound is actually in the order of log N. Furthermore, we construct an optimal code named fractional repetition code, FRC. So in the first step, we partition the workers into N over D groups, and each group stores the same D data partition. For example, the ith workers will compute the sum of partial gradient evaluated on consecutive D data partitions. So clearly, based on this construction, the recoverability is guaranteed by the fact that there exists one non-struggler worker in each worker group. And a simple union bound argument gives us the following computation load, which is asymptotically optimal as n goes to infinite. The decoding is straightforward, and we only need to sum the received results. Then let's look at this scenario. We consider the approximate recovery with a given error. So here, epsilon is the multiplicative error. So in this scenario, we have this following result. Suppose that out of n workers, S equals delta n are strugglers. So the minimum computation load satisfies the following inequality. The result shows that the recovery error provides a logarithmic reductions of the computation load from log n to log n minus log n epsilon, log epsilon n. For example, if the struggler tolerance is S is proportionally to n and the error is in the order of 1 over log n, then the minimum computation load is actually log n. While the existing Bernoulli gradient code can achieve a computation load of log n, which is far away from the optimality. So the question here is that, can we design more efficient gradient coding scheme? Luckily, we have a positive answer. We propose a type of code called batch vector code. So it consists of two steps. In the first step, we partition the original data set into n over b batches with the size of each batch equal to b. And in the second step, each worker randomly choose the batches based on a degree distribution p. So we reverse get the degree from a distribution, and then we randomly choose some batches from that is equal to that degree. So theoretically, we show that under the following modified Soliton distribution and the choice of batch size b, the BRC batch vector code with appealing decoding algorithm can achieve a decoding error epsilon with high probability and average computation load shown here. So which is asymptotically optimal. Finally, to evaluate our proposed coding schemes, we conduct experiments on the logistic regression problem with almost 20 million data samples and over 1 million features. So we run it on the Ohio Supercomputer Center, and then from the figure, we can see that our proposed algorithms, BRC and FRC, converge much faster compared to the state of art in 20 to 50% in time. To conclude today's talk, we focus on the new frontier gradient coding computation in migrating slow machines in distributed and large-scale machine learning problem. So currently several limitations of traditional coded computation in machine learning application. So we propose a new frameworks and design the approximate gradient coding that is theoretically optimal. And from this talk, we can see that the power of design efficient coding scheme in the machine learning applications. So that's it for today's talk. Thank you.